For today's lesson on interior angles of polygons, you are going to need 3 half sheets of paper. These can be any type of paper, scratch paper, notebook paper, computer paper, whatever, but you're going to need 3 sheets of paper. Scissors would probably be helpful as well, a lot easier than ripping it off, and then a pen. Obviously, throughout the entire lesson, you should keep track of these conjectures, sketches of what we're doing, and then the proofs that we do in your notebook. There will be an activity at the very end that you will need to complete for the participation points that you will show me at class next week. And that is how you'll get credit for this online class. Let's go ahead and get started. The first conjecture that we're going to look at is that the interior angles of a triangle sum to 180 degrees. This is something that we've all talked about, even in that first night of class, and a lot of you guys have known since probably you were in elementary school. So I need you to take one of your half sheets of paper and cut out a scalene triangle. Try to use most of that half sheet of paper. If your triangle's too small, it's going to be harder to do what we're going to do with it. So definitely try to make it about the size of a half sheet of paper. Throughout this entire video, you can obviously pause, catch up, and then continue. You don't need to obviously stay with the video. I just don't want the video running forever. So I'm going to keep going. Once you have your triangle drawn, it should look like this. I want you to go ahead and number the 3 interior angles. I just did the numbers 1, 2, and 3. A lot of times we call angles by their Greek letters, so you can definitely do that as well. You can label however you want, but make sure you label the 3 interior angles. Okay, then once you have this triangle with the angles labeled, I want you to go ahead and rip the angles apart. They should now look like this. You can still see my 3 angles. There's 1, 2, and 3. But I no longer have the shape of a triangle. I just have the 3 interior angles. Now, we have our conjecture at the top of the slide that says the interior angles of a triangle sum to 180 degrees. Let's go ahead, arrange these angles so that they are all next to one another. You should notice they make a straight line, and we know that a straight line or a straight angle is 180 degrees. So you just showed that the 3 angles of a triangle sum to 180 degrees. Now, unfortunately, this is an excellent activity, an experiment that you can do with elementary age kids, but as part of our college level math class, we want to be able to actually prove why this works. We don't want to just show, oh, it happens to work with this particular triangle that we cut out on this half sheet of paper. So let's go ahead and put a proof in our notebooks of why this actually works. Why do the interior angles of a triangle always sum to 180 degrees? Notice, it's really hard for me to draw on my iPad first of all, but I have a triangle here. The angles are still numbered 1, 2, and 3, and I actually extended the base of the triangle to be one parallel line, and then I drew a parallel line, notice the signs here to show that they're parallel, directly on top that touched the other vertex or corner of the triangle. The reason why I did this is because I know, and I can see from this picture, that angles 3, 4, and 5 together make a straight angle or 180 degrees. So I'm going to use that idea in my proof, in addition to some of the angle types that we learned about in class last week, to prove that the angles 1, 2, and 3, the three interior angles of the triangle, also add to 180 degrees. Okay, so first of all, I know that angle 5 is congruent to angle 1 because of a special type of angle that we learned about last week. Notice if this green line here is a transversal, angle 1 and angle 5 are inside the parallel lines on opposite sides of the transversal, which means they are alternate interior angles. Similarly, we know that angle 4 is congruent to angle 2 because of the exact same reason. It's just a different transversal. Here we're on this transversal, but angle 2 and angle 4 are still inside the parallel lines and on opposite sides of the transversal. So they too are alternate interior angles. Now, we said when we first opened this page that the measure of angle 3 plus the measure of angle 4 plus the measure of angle 5 had to be 180 degrees. They are technically a straight angle, linear paired, even though there's 3 of them, so it'd really be like a linear triplet. So a straight angle is probably the better reason. They're straight line, basically. So because angle 5 is the same as angle 1, I can replace the measure of angle 5 now with the measure of angle 1. And because angle 4 is the same as angle 2, I can replace the measure of angle 4 with the measure of angle 2. Keep the measure of angle 3 as is. I know that this must also be 180 degrees by substitution. You just proved that the 3 interior angles, 1, 2, 3, of a triangle must always sum to 180 degrees. Nice work. Now we need to look at more polygons though, because as we remember from our concept map we made together in class, triangles are just one tiny subset of polygons. Let's go ahead and look at quadrilaterals next. Our conjecture is that the interior angles of a quadrilateral will sum to 360 degrees. Our reason for this is when you traced those 6 shapes into your notebook at the end of last week's class, you should have noticed that all of the quadrilaterals summed to 360 degrees. We're going to go ahead and see if this is always the case. In order to do this, take your second sheet of half paper and draw a convex quadrilateral. Remember, that means that all interior angles are less than 180 degrees. You can draw a square, rectangle, rhombus, kite, whatever you want. And technically, you can just cut it out. You don't even need to necessarily draw it. Just do 4 straight edges with your scissors and you'll be good to go. I'm going to go ahead and pull mine up here. Oops. There we go. And then just like with the triangle, we're going to go ahead and number our angles. So I did 1, 2, 3, 4. You can see those interior angles there. Just like with the triangle, we're going to go ahead and rip these interior angles apart. So your next step would look like this. Notice I still have all 4 interior angles. They just no longer make a quadrilateral. However, go ahead and arrange them together. See what they end up making. Here mine are. What does that look like? You're right. It should look like a circle because circles are also 360 degrees. Notice the 4 interior angles of the quadrilateral sum to 360 degrees, just like we thought. Remember though, this is not a proof. This is a great way to show elementary students that this will work, but it is not considered a mathematical proof. My question to you is, will this work as well for concave quadrilaterals? That's what your third sheet of half paper is for. Go ahead, draw your concave quadrilateral, cut it out, and number the angles. Again, pause this video until you are done, and you can see what happens with the angles. Here's my concave quadrilateral. I'm going to kind of go through this quickly, hoping that you did it on your own. So I did cut apart or rip apart the angles, and I arranged them. Yes, the one was greater than 180 degrees. That's my angle 2 right here. You can see that's definitely bigger. However, the 4 angles together should still make a circle because the interior angles of a quadrilateral sum to 360 degrees always. Now, why will this always work? How can we prove that the 4 interior angles of a quadrilateral always sum to 360 degrees? We are not going to introduce parallel lines and all of the types of angles that we learned about last week. Rather, we're going to use the proof that we just did with the triangle, and we're going to prove why this will work. You can always go back to proofs that we've already done in class together or ones that you've even done on the homework, and you can use them. You don't always have to reprove them every single time. So what I'm going to do is I'm going to draw in a diagonal connecting 2 of the vertices of my quadrilateral. Notice I just split this quadrilateral now into 2 triangles. This triangle has these interior angles. But using the proof that we just did, I know those 3 angles will sum to 180 degrees. Similarly, this bottom triangle has these interior angles here, here, and here. But again, because it's a triangle, I know that they will add to 180 degrees. Now notice, every single interior angle of my quadrilateral is now accounted for. So if I sum together the 180 degrees from my first triangle plus the 180 degrees from my second triangle, I will arrive at the 360 degrees total for the interior angles of the quadrilateral. Now, technically, I have a convex quadrilateral drawn here. You can also prove this for concave quadrilaterals. You just need to be a little bit more particular in terms of which diagonal. Notice here I could have drawn in either of the 2 diagonals, connected any of the pairs of vertices. However, with the concave quadrilateral, you need to make sure you don't leave the shape when drawing in the diagonal. So you need to just make sure that you're connecting the appropriate set of vertices when proving it for a concave quadrilateral. Can we continue with polygons with more numbers of sides? For example, a pentagon or a hexagon? In your notebook, I want you to copy down this table. So you have the number of sides ranging from 3 up to 10, and then I want you to include an n row at the bottom. That can be for n number of sides. That's a variable. And then I want you to complete the sum going all the way up. You can think about the proof we just did for quadrilaterals, and you can extend it to polygons with more sides. Think about how many triangles would you have in a pentagon? How many triangles would you then have in a hexagon? and so on. You can prove this for any n-sided polygon. Your challenge is to then come up with an explicit formula down here at the very bottom that would work for any n-sided polygon. How do we determine the sum of interior angles for any n-sided polygon? This is the table that I will be checking for your participation points for this online class. So please be sure to have this with you next week at class. Have a wonderful week.